Ladies and gentlemen, I am delighted to have the opportunity to talk to you today about the exciting field of fusion energy and its potential to revolutionize the way we generate and use energy. Fusion energy has long been considered a holy grail of energy research and development, and the progress made in recent years has brought us closer than ever before to realizing this goal. At its core, fusion energy is based on the same physical process that powers the stars, the fusion of atomic nuclei. In a fusion reaction, the nuclei of two atoms combine to form a heavier nucleus, releasing energy in the process. This process occurs naturally in the Sun and other stars, where the heat and pressure are sufficient to sustain the fusion reaction. Scientists have been trying to replicate this process on Earth for decades, and significant progress has been made in recent years. One of the primary advantages of fusion energy is that it is virtually unlimited and produces no greenhouse gases or long-lived radioactive waste. Unlike traditional forms of energy such as fossil fuels or nuclear power, fusion energy does not produce harmful emissions or contribute to climate change. In fact, a single liter of seawater contains enough deuterium, one of the isotopes used in fusion, to produce the same amount of energy as 300 liters of gasoline. Despite the potential of fusion energy, there are still significant technical challenges that must be overcome before it can be a viable source of power. One of the main challenges is achieving the high temperatures and pressures required to sustain the fusion reaction. In a fusion reactor, plasma, a state of matter that is created by heating a gas to extremely high temperatures, is confined and controlled using magnetic fields. To sustain the reaction, the plasma must be heated to temperatures in excess of 100 million degrees Celsius, creating a state of matter that is hotter than the center of the Sun. Another challenge is finding suitable materials that can withstand the extreme conditions inside a fusion reactor. The high temperatures and radiation levels can cause materials to degrade or become radioactive themselves, which can pose a hazard to workers and the environment. Research is ongoing to develop materials that are suitable for use in fusion reactors, such as advanced ceramics and superconducting alloys. Despite these challenges, there has been significant progress in the field of fusion energy in recent years. In 2020, the European Union and the United Kingdom launched the construction of the ITER fusion reactor, which is currently under construction in southern France. When completed, ITER will be the world's largest tokamak, and it is expected to produce 500 megawatts of fusion power for up to 1,000 seconds, a major milestone in the field of fusion energy. In addition to ITER, there are numerous other research programs and initiatives around the world that are focused on developing fusion energy. These include private companies, such as General Fusion and Commonwealth Fusion Systems, as well as government-funded research programs in countries such as China, Japan, and the United States. One of the most exciting recent developments in the field of fusion energy is the emergence of new, innovative fusion concepts that could potentially overcome some of the technical challenges of traditional tokamak designs. These concepts include magnetized target fusion, laser-driven fusion, and inertial confinement fusion. These new approaches offer exciting possibilities for developing more compact, efficient, and cost-effective fusion reactors. So, what does the future hold for fusion energy? While it is impossible to predict with certainty, the prospects for fusion energy are truly exciting. If successful, fusion energy could provide a virtually unlimited source of clean, safe, and sustainable power for generations to come. It could also help to mitigate the impacts of climate change by reducing our dependence on fossil fuels. In addition, fusion energy could have a significant impact on global energy security, reducing our dependence on foreign oil and gas imports. Fusion energy could also help to provide power to remote or off-grid locations, enabling access to electricity for millions of people around the world. There is no doubt that the development of fusion energy will require continued investment and support from governments, private industry, and academia. It is a long-term, high-risk endeavor that requires sustained commitment and collaboration. However, the potential benefits are enormous, and the progress made in recent years is truly remarkable. In conclusion, fusion energy represents one of the most exciting and promising areas of research and development today. With continued investment and support, we could be on the cusp of a new era of clean, safe, and sustainable energy. I hope that this introduction to fusion energy and plasma physics has been informative and engaging, and I encourage you to learn more about this fascinating field. Thank you for your attention.